Hello everyone, today we're going to do a couple things. We're going to do A9 and A10. A9 and A10 are going to discuss two different things. A10 is going to be one-sided limits and talk about discontinuity, which I'll show you what that is. But then the first thing we're going to do, A9, is limits at infinity. We discussed this in the year already, but I want to go over it and we'll go over all the details you need to know to figure out these limits. So the two key things is the limit as x approaches infinity is what your right tail is doing. And the limit as x approaches negative infinity is what your left tail is doing. Okay, so if you get your A9 packets out, this is what it'll look like. Here is the notation. Okay, so we're just going to look at limits as x approaches infinity and negative infinity. So first of all, I'll let you kind of read this stuff on your own. But if you have some type of polynomial or anything that's not a rational expression, you just need to figure out what's going on with the graph and then look at what they're asking. So first of all, the graph of 3x cubed is going to look like this, somewhat. Okay, it'll probably come up and it'll come down, but this is what it's going to look like. So the key is the limit as x approaches infinity. That is what my right tail is doing. Well, what's my right tail doing here? It's going upwards, so your answer would be infinity. So this says find the limit as I approach infinity of this curve. So key is hey, what's the limit as x approaches infinity? Now these limits are different than the limits we've been doing. If the limit is ever approaching a number, a real number, we go over that thing I said yesterday. And in number one, you algebraically sub it in. If you get a number, that's it. If you get a number over 0, it doesn't exist because it's a vertical asymptote. And if you get 0 over 0, you can simplify it. Then I said, hey, if you can't do any of that, look at a graph. And finally, a table is something that will always work. Okay, now these are going to be different. So when you see the limit as x approaches infinity, you need to know that is what my right tail is doing. So find out what your curve is doing. Well, it's a negative x squared. So my right tail is going down. So this answer is going to be negative infinity. So this says, hey, the limit as x approaches negative infinity. This is my left tail. Well, if you look at this cube or this square or curve, it's the same one as this. So the left tail of this is going downwards, so you put negative infinity. That is what this limit is approaching. It's going downwards. Here, this is what my left tail is doing of this same curve up here. Well, my left curve is going down, so I put negative infinity. And this one is a negative x cubed. You need to know a negative x cubed graph looks like this. And so this is what is my left tail doing while it's going upwards. So you put infinity. Now, finally, they're not always going to be infinity or negative infinity, because if you look at this, what's the graph of 3 look like? Well, it looks like this. What is my left tail doing? Well, it's continually going towards 3. Okay, so that follows the rule, the limit of any constant is always itself. All right, so if you just have a basic function, just know that I'm asking what the tails are doing. Now, if you have a rational expression, which means x's are on top and bottom, or just on bottom, this is what's going to happen. If your degree on bottom is bigger, okay, then it's going to end up being 0. All right, so if you have 3 over x, this is going to end up being 0. Now, here's the real reason why. Instead, you can kind of read, but this graph is going to look like this. If the degree on bottom 0, remember when we talked about horizontal asymptotes, and I said if the degree on bottom 0, it's going to get closer and closer to 0 because as x gets bigger and bigger, this number right here is going to get smaller and smaller. So if you look at my right tail, it's getting closer and closer to 0. So the limit as x approaches negative infinity, you need to understand that's my left tail. And then if my degree on bottom's bigger, it's going to end up being 0. Once again, you could graph it, but you'll see that it gets closer and closer to the axis. And finally, just make sure you know that if you ever have a negative exponent, you can bring it down and make it positive in the denominator. So 3x to the negative second is the same as 3 over x squared. And in this case, since the degree on bottom's bigger, the limit is 0. Okay? So now what happens if you have x's on top and bottom? So I give you kind of like all the rules up here, but what we're doing is it's very similar to horizontal asymptotes. We found those already. How do you find horizontal asymptotes? You compare the degrees. If the degree on bottom's bigger, it's 0. If the degrees are the same, it's the ratio of the lead coefficients. Now, if the degree on top's bigger, there is no horizontal asymptote, which means it's either going up or down. And what we do is we take the two biggest powers, reduce it, and we find what that tail is doing, and that's going to be the same as our original function. So if I said, hey, what's the limit as x approaches infinity? I'm saying, what is my right tail doing of this? Well, if it's a rational expression, if the degree on bottom is bigger, that means your horizontal asymptote is 0, so it's getting closer and closer to 0. Limit as x approaches infinity of this function, well, this is my right tail. If the degrees are the same, it's the ratio of the lead coefficients, which is 1/3. Now, if I ask you, okay, find the right tail or left tail, if the degree on top's bigger, what you're going to do is you're going to take the two biggest powers and you're going to reduce it. You can take an x squared out of each of those and you get x over 3. Well, the curve x over 3 is just a line like this, right? So my right tail of this reduced function is going upwards, therefore my answer is infinity. So let's look at this one. It's the same function, but I want to know my left tail. So you reduce these two to make it be x over 3. That's just a linear function like this. And what's my left tail doing? It's going downwards, so you put negative infinity. What's my left tail doing? If the degree on bottom's bigger, well, if the degree on bottom's bigger, your tail's getting closer and closer to 0. And you can graph it and see this too. Like you could graph these two, and in this one, the right tail's going upwards, and in this one, the left tail's going downwards. Here, the left tail's getting closer and closer to 0. Now for f, what's my left tail doing? Well, the x cubed are the highest powers, and since they're equal, it's the ratio of the lead coefficients, which is 3. Okay, the last one, which is kind of tricky, ends up dealing with e's. So I kind of want to show, actually, let's talk about ln's real quick. Okay, the natural logarithm. First of all, the graph of the natural logarithm looks like this. If you remember us going over the function, the domain of this is that x must be bigger than 0. So what's going to happen is, if I said, hey, what is my right tail doing in ln of x? Well, that's this guy right here, which is going upwards, so I would say infinity. What's the limit as I approach 0 from the right side? Well, I'm going downwards, so since it's approaching an asymptote, I could say negative infinity. Here's the tricky part. I know I always say that ln of, or limit as x approaches negative infinity is my left tail. Here's where that notation goes a little awry, because I'm asking what's happening to the graph as I move left. Well, the thing is you can't put any negative numbers in here. The graph does not exist anywhere to the left of the y-axis there. So in that case, it does not exist. Finally, you get to some e's, okay? The thing with e's is just graph it. Like if I said, okay, what's the limit as x approaches infinity of e to the x? Well, if you graph it, we know it's just an exponential function with a base bigger than 1, so it's a growth model. What's my right tail doing? Well, it's going upwards, so you put infinity. Here's e to the x. I want to know what my left tail is doing. Well, if you look, it's getting closer and closer to 0. So what's 2 e to the 2 over x? Well, if you graph it, it's going to look like this. So what is your right tail doing? Well, you just look at the graph and say, hey, it's getting closer and closer to 0. This is the left tail of this same function, which is going upwards, so you'd put infinity. E to the negative x, well, that looks exactly like this same function. So what is my left tail doing? It's going upwards, so you would put infinity. And what is my right tail doing of this? Well, it's getting closer and closer to 0. All right, finally, with limits as x approaches infinity, there's going to be a real world application that says something like this. A business manager determines that T months after production begins on a new product, the number of units will be P,000, where P is this. What happens to production in the long run? You need to know in the long run is the limit as T approaches infinity of this function right here. So that's what you need to know is, if I ever say in the long run, it's the limit as t approaches infinity. Well, if we look, the degrees are the same, so it's the ratio of the lead coefficients, so it would be 6, and it's in thousands, so it's going to be 6,000. So that's what's going to happen in the long run. All right? So the main thing with limits as x approaches infinity or negative infinity is it's the tails. Okay, if you would, go ahead and get A10 out. We're just going to talk about this just a little bit more. Make sure we know what one-sided limits are. So here's a graph, and I'm going to say, hey, what's the limit as I approach -2 from the left? So here's -2. As I approach it from the left, I'm getting closer and closer to 4. So what happens when I approach -2 from the right? So I come over here and I approach -2 from the right, which is 4. Well, if you ever approached the left and right the same, the limit is still 4. Now, as a conceptual understanding, remember the limit's what's happening around the x value, not at it. This graph actually is down here at -5, but the limit is what's happening around it, so that's why the limit's 4, because that's what I'm approaching from the left and the right. So if we look at 3, what's the limit as I approach 3 from the left? Well, as I approach it from the left, I'm getting closer and closer to the y value of 9. The limit as I approach 3 from the right, well, I'm getting closer and closer to 3. And since I'm getting two different numbers, I'd say the limit does not exist. Okay, the next one, evaluating one-sided limits. No matter if it's one-sided or not, if I find the limit as x approaches a particular number, the first step is to plug it in. I would get 3 on top, 4 on bottom. If you ever get a number, that's your limit. It's 3/4. So I'd plug 2 in, and I would get 0 on top and 8 on bottom. But 0 over 8, that's okay. That is equal to 0, so that limit is 0. So the other case is, all right, well, I'm going to do this one-sided limit. I'm going to plug -1 in, and I get a number over 0. Now, normally I would say the limit doesn't exist if I'm just looking at a particular limit. But if it's one-sided and you're approaching an asymptote, I need you to tell me whether it goes up or down. Okay? So if you plug -1 in here, actually you want to plug in like -0.99. Okay? Actually, no, they want you to plug in -1.01. So what you do is you plug these in here, and you find out if you're going up or down. If these numbers are getting bigger, then it's going to infinity. If these numbers are getting smaller, it's going to go to -infinity. So I'm going to let you plug those in there. Now, with a piecewise function, this is a little different. I want you to change all these to be positive ones. Sorry, I'm trying to write these up. I made some mistakes at times. So anyway, with the piecewise functions, remember this says if I have any number less than 1, I plug it in here. Any number between 1 and 3, I plug it in here. Bigger than 3 is this. So if I'm looking at the limits of this piecewise function, essentially what I want to do is find out, do they meet up at the same place? So if I'm looking at the limit as I approach 1 from the left, I plug 1 in here. I'm getting closer and closer to 2. All right? So this curve is getting closer and closer to a y value of 2. Now I plug 1 into this function, because if I'm approaching it from the right, I'm at the numbers bigger than 1. So I plug it in here, and if I plug 1 in here, I get 2. So that means that this limit exists, and it's going to be 2. So to find out if a limit exists in a piecewise, we want to know, do these things meet up or do they not? Because if they don't, you're going to get this picture to where it's a jump discontinuity, and that's one of the reasons a limit would not exist, because I'm approaching two separate numbers. So let's look at this one. If I approach -3 from the left, that means I'm smaller than 3. Oh, sorry, -3. If it's -3, that's less than 1. You just plug it in here and you get -2. The limit as I approach 1/3, -1/3 from the right, well, it's in here. Since -1/3 is less than 1, you just straight plug it in and you get 2/3. Now, if I said find the limit as I approach -3, well, you just plug -3 in and you get -2. Okay, we're going to do some others and some homework that I'll go over with you later. Okay, next thing is we're going to go right down here, and we're just going to talk about determine whether a function is continuous. To see if it's continuous, all you want to do is see if there's an actual point in there. If you plug -1 in and you get a point, you say, yes, it's continuous at that point. Now, if I plug 2 in, I get a point. So I would say, yes, it's continuous. Where is this graph not continuous at? -5. So this is continuous everywhere but -5. But all this question's asking is it continuous at 2? Is this graph continuous at -5? Well, if you plug -5 in, you get a 0 on bottom, which means it's either a whole or a vertical asymptote. So this is no, it's not continuous. Now the next question says determine the values of x to where it's not continuous. This doesn't have any discontinuities. It's just a smooth curve, so this is none. That has no discontinuities. This one, if you graph it, you'll see that there are 2 discontinuities at 0 and 5. So to find discontinuities, you essentially set the denominator equal to 0 and solve. And then over here, you would get plus or minus 3 as my discontinuities. Okay. Last page. Piecewise functions. We want to know if these things are continuous. This is very similar to finding a limit. If you want to see if piecewise functions are continuous, you could just graph it. So you could graph x squared minus 2x when x is less than -2. So what you do is you plug -2 in here and you get 8. So this graph is going to leave off at a y value of 8. So then if I plug -2 in here, this graph is going to pick up at 3. So is this graph continuous at -2? The answer is not continuous at x equals -2. And if you look, it's because when you plug these 2 numbers in here and here, you get 2 different y values, so they're not going to meet up. Okay, over here, there's 2 different possible discontinuities. So if I plug one in here, I get a 2. If I plug one here, I get a 2. So that means these 2 things actually meet up. But when I plug 3 in here, I get -9 plus 4x is 3 minus 2 is 2. So this thing is going to end up at 2, but this one picks up at -1. So it is not continuous at x equals 3. All right, so that's talking a little bit about continuity. Now we're going to get some real world applications here, and they're going to say, hey, this ruptured pipe spills some oil. The width of the oil is going to be this function to where x is the distance, okay, in meters from the rupture. So they're going to say, how thick would you expect the oil slick to be at 5? All you're doing is you're going to take 5 and you're just going to substitute 5 in there. And then you get whatever that answer would be. Well, the thing is I want to know, where is it going to be at 0? Well, the issue is, sorry, one of the kitties. The issue is if I plug 0 in, I get 0 over 0. Now remember, if you're finding a limit, that means you can take an x out of everything. So if you take an x out of everything, you would get an x squared plus 3 over x squared plus x plus 4. So take an x out of everything up here and now plug 0 in. And you get 1.5 on top and you get a 4 on bottom. And that'll tell you what the thickness is there. And lastly, remember, when I say in the long run, I'm talking about the limit as x approaches infinity. Well, if you look, the degree on bottom is bigger, so this answer is going to end up being 0. And hopefully that'll make sense. If you have an oil spill, eventually it's not going to spill and just keep going on forever and ever. It's actually going to thin out to where it stops and its thickness is 0. Okay, guys, I have one more lesson to teach you with trig, but I'll do that after May 1st because that's when I'm going to go back to school and do some stuff. But work on these packets, work on the homework I gave you, which hopefully if you do not remember, it's these problems right here. And the book, once again, is Sydney Worth posted it as one of the first things posted in my Google Classroom. Thank you and good luck.